Okay, thank you. Yeah, so so one thing before we get going, I probably should have had a talk with Thiago prior to the grading. I noticed a number of grades that were kind of low, and so I looked at some of those, and I don't know if Thiago was like giving partial credit and stuff like that. So for some of the some of the problems. So anyway, so I had a talk with him and kind of established a rubric for the grading. I mean, so in my mind, the process is worth most of the credit. So if you have a decent description of what you were trying to do in solving that homework problem, that's worth at least 75% or so. And then, if you knew like where to insert the numbers correctly, that's worth another 10 or 15%. And then if you get the exact answer, that's worth the last 5 or so points. So if any of you had some real heartburn with the grading on the last assignment, Thiago said he'd be glad to have a look at it and reconsider. I think he's doing a conscientious job. I notice he's giving some good feedback and comments on the homework, so he's putting the time in. I just, I don't feel, if you get a 0 on a problem, that means you could turn in nothing and get the same 0. But if you have some work there, I think you ought to get some credit for doing the work. So, or at least that's my philosophy. So, again, if you have had any question or issue with that, please, see Thiago, and he'll be happy to sort that out with you. And if you need extra, if you were deserving of extra credit. Okay, so we are again talking about imaging, and so what we did was to form the ray trace relations. And the next thing that we're working on was the paraxial imaging relations. And so in the paraxial imaging relations, we basically were manipulating the phase of our fields. So we have a phase for what we were calling the primary image, and a phase for the secondary image. Most of the time this one will be a virtual image, and this one will be a real image where light is converging to that point. However, this the secondary could still, if you're reconstructing again with the phi sub p that equals phi sub r, then the image with good fidelity is going to be phi 3, and if you imaged if phi p were equal to phi r star, then the image with good fidelity is going to be phi 4, which generally represents a form of conjugate image in the reconstruction. All right, so we found that what we needed to do was we had our this U3 and U4 had a say a constant out here, which was a product of all the different field terms. So we'll just represent that as, say, a constant. The main part is the phase function. So we have a minus j phi p minus phi r plus phi o for the object field, and we have a constant for U4, exponential of minus j phi p plus phi r minus phi o. All right, and so what we said here in coming up with the solution was that, so these are based on the construction and reconstruction parameters, right? which are represented by phi r and phi o are your construction, and phi p is the reconstruction. And then what we said, in order for this to form an image, the field that we generate from this must, again, converge or diverge from some point. All right, and so for that we said that we had a phi 3 here, which is kind of a second solution. So this would be, say, the first solution for this phi 3 and phi 4, again, based on the construction and reconstruction parameters. The second one is based on the notion of imaging, in which, again, the field should converge or diverge to a particular point. And so this then is equal to a pi over lambda 2 z3. And so the point is x3, y3, and z3, the image point that the light is, again, converging or diverging from, times a quadratic here, x squared plus y squared minus 2x x3 minus 2y y3, okay, for the for that image point. And so what we end up doing is, again, so we have, again, all of this, for instance, here is phi 3, and we'll call that 1. And so for imaging, what we said is that phi 3, 1 must equal to phi 3, 2. All right? The two have to be kind of merging upon one another. And so, so again, this gives us a big expansion. I won't go through all that again. It's similar to this, except, it has phi, xp and xr and xo and all the other terms in it. But now what we can do is, so there will be x squared and y squared terms here. So we can set those equal, and there's linear terms. We can set those equal. And when we do that, we can then form a solution for the coordinates of our image point, right? And so the solution here is that we have x3 now is equal to xp z0 zr plus mu, and mu is equal to lambda 2 over lambda 1, so this is the construction wavelength and this is the reconstruction wavelength. Again, they don't have to be equal, and in many cases they will be different, and so we'll need to deal with that. So we have this ratio of wavelengths mu, x0 zp zr minus mu xr xp zo. I'm sorry, zp zo. Yeah, very good. There is some symmetry in this. And then we have zo zr plus mu zp zr minus mu zp zo for the denominator. Of course, the y3 is going to look the same, except we have, yp and zo zr plus mu yo zp zr minus mu yr zp zo, all that over the same denominator. So let's call that our ZD, or the denominator, since that'll be repeated. And then for Z3, that is equal to ZP, ZO, ZR over this ZD. Okay. All right, so again, so these are the image coordinates, the paraxial image coordinates. And remember how that was formed, right? That was formed by expanding this spherical wave that we have into, an expansion, all right, for lack of other words. And then we had these radicals in there. And so in order to get rid of the radicals, we used the binomial expansion. And so we took basically the first term of that binomial expansion, and that is really what this paraxial image gives us. Okay, it's that first expansion term in the phase that we have here. All right, so this is actually the 1/2 b term from the binomial expansion. All right, so again, that might be a nice little question to ask: is where do these terms come from? What do they mean, and so forth. And again, this is really the important part here. The algebra is sort of cumbersome, but doable. But nonetheless, I would like you to appreciate the way in which this solution was obtained. Okay, because it could be applied to some other things that you may be working on as well. All right. So this is the again paraxial image coordinates for the primary image. Okay, and then we also have for the secondary image, we have a x4, y4, and z4 that are somewhat, they are similar in form, but the signs are kind of reversed to some degree. So here we have xp, zo, zr, minus, instead of a plus, mu, xo, zp, zr, and then plus mu, xr, zp, zo. And we have, again, a denominator, but this one has different signs. So we have zo, zr, minus mu, zp, zr, plus mu, zp, zr. So we can call this zd3, and this one here is zd4, okay, for this secondary image. Y4 is pretty much the same, except you put y's here, yp, zo, zr, minus mu, yo, zp, zr, plus mu, yr, zp, zo, all of that over zd4, and then z4 is going to be equal to zp, zo, zr over zo, zr, I'm sorry, let's just call that zd4 since we already went through that trouble, like so. Okay, so again, oops. YR.
Defining the ZD4, the last term should have a
Oh.
Z naught rather than 0.
Yeah, so that one should be ZPZO, right. Good, you guys are on your toes, very good. Okay, so these are the paraxial image points. And by the way, there's a paper, I'll put this online. It's kind of an old paper, but where this was first formulated back in the 1965, so 50 years ago. Wow, half a century ago. And so, again, holography was just kind of taken off with the advent of lasers. And so there was really a lot of interest in how to model these and to incorporate these. And so I have different notation, but the ideas were kind of taken from this particular paper here. So I'll put that online so you guys can read that. It's worth going through as well. Now, there's another formulation for imaging, kind of a paraxial imaging. And this is for kind of axial image points. So this is, I don't know, I guess holographic needs to be in there somewhere. So holographic axial image point relations. And so what I mean by that is, for instance, if we have a, and these relations are useful and used in a number of papers on describing holographic imagery with holographic optical elements. And so here again is our film during the recording phase for the hologram. And say, for instance, there is again, these are all axial. So we have a reference point here, which is located z sub r, say, away from that hologram plane. And then we may have let's say if we have a converging wave here as the object wave converging to a point which is z sub o out here. So this is, again, during the construction. And then during reconstruction, we have now, so now we have the hologram itself, the holographic optical element or hologram. And now we place a point P out here, which is maybe located at a different axial distance away, ZP, and that converges down to a image point located some distance Zi away from the hologram. Okay, so in this situation, and these waves, you know, the reference and reconstruction waves could be, you know, planar waves and so forth, and shifting in wavelength and things like that. So when we have this condition, we can actually write the relationship as 1 over Zi minus 1 over Zp is, sorry, I didn't know what that moan meant, plus or minus mu 1 over Zo minus 1 over Zr. So again, these are kind of like our imaging relations that we had before. And this that we have here is kind of equivalent to a, call that, say, a holographic focal point or focal distance. All right, and so we can now use this kind of relationship the same way we used, you know, the imaging relation where, you know, we have 1 over, say, di is 1 over d plus 1 over f. So we have the same thing here if we use this now instead of, you know, the focal length that we would have, say, for a refractive element, and in this relationship. So this formulation is used, and we'll come back to this a little bit later in discussing some of the aberrations in reconstructing holographic images. It's a little bit more convenient because now you can talk about kind of radii here as well. If you add an angle here, cosine theta, as we'll do later, you can end up getting some, you know, the xy components of that as well. But again, so if you want just quickly to find out where the image point is and knowing the axial positions of these points, you can use this relationship as well. Okay, so now that we have these paraxial imaging relationships, we can do a couple of things. All right, so the first thing that we'll do is, you know, sometimes you'd like to know, like, you know, what sort of, you made your lenses in the lab yesterday and today, and so you may want to know, like, you know, what's the magnification that you can get, you know, when you play with this. And so we can derive some relationships using these paraxial image relations that we have. We can derive relationships for the magnification characteristics of that hologram. So first thing that we'll look at is, say, a lateral magnification. And so here, again, here's our hologram looking something like that. Out here, and we have an object point. And so what if, if that object point were to move in this, or, if we had a reconstruction point, we can think of the reconstruction point. I don't know, for some reason I used delta x0. But, if we change that, say, object point, how much does the image point change? Right? So here might be x3, and then we might get a different delta x3, right? Something like that. All right, so what is our definition of lateral magnification? And this can be for, either the primary or secondary. Basically, that's going to be, if we change this object height here, say dxo, how much does the dx3 and dx4 change? Okay. And so, and similarly, we could have for the y's. But so what we could do then is simply differentiate this relationship that we have here with regard to the object location. All right. And so what we would end up with there is a lateral magnification, which is equal to 1 over 1 plus z0 times 1 over mu zp minus 1 over zr, okay, in the denominator. All right. So so one thing we could see here is that if lambda 2 is equal to lambda 1 and zp is equal to zr, then the magnification is equal to, the lateral magnification is equal to 1, okay, which is what you would expect. If you're not changing anything, from the construction conditions, then you shouldn't really see any difference in the reconstruction, all right? So that's our the lateral magnification. We can also have an angular magnification, all right? And so let's look at that for a second. All right, so for angular magnification, we will have something like this. All right, so again, we have our hologram out here, and we can look at a change in angle. So basically, we have x0 again, and we go to a dx0, and that we can also say is related to angles that we have, say a alpha 0 angle in that change in that height of that object. And then what we'd like to see is how much of a change in height in the image would we expect. So here might be x3, and then here is dx3, and here is an alpha 3. And so our definition for this angular magnification would be something like the change in the image angle, d of x3 over z3, say the tangent. So we're looking at that change relative to the dxo over zo, all right? And when we, again, take our paraxial imaging relationships and perform this differential, we end up with something quite simple. It's just equal to mu. All right. So the angular magnification is just equal to the ratio of the wavelengths that we would have between the construction and reconstruction. So again, this is the reconstruction and construction wavelength. So if there is a difference, we will see a angular magnification change. If there's no difference in those wavelengths, we won't see any. All right? Okay, and then finally, we could also have, just like in refractive and reflective imaging, we can have a longitudinal magnification. And so here, here we have our hologram again. And so what we do here is if we have a object out here and then we move it one direction or another, so we have a delta z0, how much does that produce a change in the image location? So here we would have, say, a different shift delta z3. All right, so again, our longitudinal magnification will derive from the paraxial imaging relationships, and this is just equal to z3 dzo, all right, the change in image with object change, and this is equal to 1 over mu d by dz 0 of z0 over 1 plus z0 times 1 over mu zp minus 1 over zr. And notice that, that this was the same as our lateral magnification. And so we can say that the longitudinal magnification is just equal to 1 over, this is for the primary image, 1 over mu times the lateral magnification squared. Just like you have in refractive and reflective optics. If you have the secondary image, the longitudinal magnification is a minus 1 over mu m lat. So this is 3, 4 squared. Okay. So again, so those are some basic relations that we might work with in evaluating holographic imaging. Okay, and give you some idea where to expect an image. All right. So let's let's do an example. Little example. Throw some numbers around here, and so we'll take a. I'll draw it here to see how all this fits together. So here we have z and x and y coming out like so. And so for the construction, we will have a reference beam here with an angle theta r equals 11 degrees. And so this is a plane wave coming from infinity going to our hologram plane. So this is the hologram plane out here. And then we'll have an object point which is out here located at 1, 0, minus 5. So here's 1 unit and minus 5 units. And we'll have a wavelength, lambda 1 equals lambda 2 equals 780 nanometers. But as soon as I tell you that lambda 1 equals lambda 2, actually the wavelength then becomes irrelevant because everything is in terms of the ratios of the two wavelengths. Okay. All right, and then for the reconstruction, so this is R. For the reconstruction, we're going to come in with a slightly different angle here. Theta p is equal to 10 degrees. So here's p, also a plane wave. So they're both plane waves. illuminating the hologram during construction and also during reconstruction. All right, so again, so we have our relationships, right? And so these are all in terms of coordinates, but we have plane waves, so we need to kind of figure out a way how to deal with those plane waves. It's not too difficult. So we have a reference wave now. So this is a plane wave, so let's just, it's just a point source really far away. So what's really far away? Well, it's all relative, but let's make it minus 10,000. Okay, that's pretty far away. And then xr then is just equal to tan of theta r times zr. And God bless you. So this is equal to minus 1943.8. And the reconstruction wave that we have, our p wave, has, again, it's zp, again, also at minus infinity. So this is minus 10,000 for our purposes. And then we have xp now is equal to zp tan of 10 degrees. And so this is minus 1763.3. So they're both, they're similar, but, they're not equal, okay? That 1 degree difference creates a bit of a difference there. All right, so let's now calculate the primary image location. All right, so usually let's do the denominator. So we have ZD3 here, so that's ZO, ZR plus mu ZP, ZR minus mu ZP, ZR. And mu is equal to 1 because we have same wavelengths. We could have changed that if we wish. And so the x3 then is, again, xp, ZO, ZR plus mu xo, ZP, ZR minus mu xr, ZP, ZO over ZD3. And so we put the numbers in there, and we end up with, I end up with a value here of 1.09027. I don't know how many figures I need to carry, but it's 1.09 or about 1.1 instead of 1. All right, and then the Z3 is ZP, ZO times ZR over ZD3. And so this works out to be minus 5 still. Okay. All right, and again, so this is kind of, it's negative, so the image point is going to be back here. So we have basically a virtual image. And so this, again, is indicated by that negative sign. Virtual image for our primary image. Let's look at the secondary image. Here, all right, so here we have a ZD4 is ZO, ZR minus mu ZP, ZR plus mu ZP, ZO. All right, so a little bit different there. And so here we have X4 is equal to 1.091356. Okay, so I didn't write it. It's similar to this, but we just reversed those signs there. So this one is positive. It's 1.09. It's a little bit different, though, okay, out here in the third decimal point. All right. So what units are these? Well, they're whatever units that we choose, really, right? So we could have centimeters, and then this would be in centimeters, and that could be a pretty significant difference in image location if we're talking, millimeters, and we're now down into microns of image difference. Okay, so it could be pretty significant as far as imagery goes. And then the Z4 that we have here is equal to plus 5.005. All right, so the plus now indicates a real image for this secondary image, as we expected, and it's off a little bit from this virtual image, okay, as well. So both of these images are slightly moved, which we would expect, right? They're not going to be in the same location as when we reconstruct, say, with the exact image location. So, so by the way, so if we're doing this imagery, all right, we can get, and this is something we'll come back to when we talk about the aberrations, but you can actually get a perfect, well, supposedly a perfect image point paraxially, you know, if we reconstruct at the construction condition. But how many times do you actually need a perfect, you know, reconstruction point? Not that often, right? Most of the time you need a reconstruction image fidelity that's consistent with whatever your viewing mechanism is. That could be the eye, or that could be a camera, or, you know, whatever else you're using. So you don't have to have exact image reconstruction, right? We can play with that, and that's often used in lens design and optical design. You use that, you can now trade that off and maybe get better performance over a larger field of view or some range of wavelengths and some other range and parameters, all right? So we're going to look at that when we look at the aberrations shortly. So, you know, getting an exact image point is really nice. You see one dot. However, that doesn't include diffraction. You still have diffraction, you know, in general. So this is going to, again, say, just like you do in the lab, right? You illuminate a certain aperture there. So even though this is saying that we're imaging to a point, there is an airy disk around there, 2J1X over X, which is spreading that out anyway. Okay, so there is some spread due to that factor as well, diffraction limited imagery. Okay, so what else can we do with these paraxial imaging relationships? All right, well, there's some other interesting things we could do. Now, one thing about a hologram, right? A hologram is a grating, and so we're going to end up with dispersion, right? And so we're going to have wavelength variation in the reconstruction, all right? So holograms actually are notoriously sensitive to changes in wavelength. Hologram image quality, I should say. Big degradation. But there are some things you could do to minimize that, okay? And we talked about one of those earlier, and we'll see why, we'll see the motivation for that. And you know, the thing that we talked about, remember I mentioned that image plane hologram, where we have a, so here's our hologram, and we had an object. I'm sorry, here we have a lens. And here we have we're forming an object. We have an object here. We illuminate that. And we end up forming a image. Out there, and that was where I said, you know, for this image plane hologram, you want to put your film to do the recording, kind of straddling the image out there, and here's your reference beam. And I said that if you do this, you can actually dramatically reduce the blurring that results when you, say, try to illuminate this or to view this either in white light or with an LED or with some type of broadband source. And I mentioned that the factor that comes to play here is this delta z0, this range or this distance of the object away from the film plane. So now we can actually derive why that's true. Okay, so let's go ahead and do that. All right, so we'll take a special case. All right, so here we have a hologram that will form, and so this is again during the construction phase, and so we'll have an object field here. We have some point out here, x0, y0, z0, and then we have a plane wave theta sub r. So here's r. Plane wave coming in from infinity, illuminating that hologram. And then during the reconstruction, we'll give ourselves a little break, and then we'll have it come in here at theta p, also a plane wave. And we're going to get some reconstruction beam coming out here. So this is our image. All right, and so again, so we have plane waves for the reference and reconstruction. So we have ZR equals ZP equals again minus infinity. But we can, again, use big angles, or I'm sorry, big distances. Or now we have the fact that we have an angle there, so we don't even have to worry about that so much. We could use the fact that tan theta r is equal to ratio xr over zr. So if we put things in terms of x over z, where we can use these angles, and we also have tan theta p is equal to xp over zp. All right, so those angles tell us something we could use as well. All right, so now if we look at our reconstruction, we can say that we have x3 is equal to x0 plus xp over zp. We kind of divide out all these different things. Again, using the fact that these are an infinity, we have a lot of terms that are like 1 over zr, 1 over zp, so they all drop out. But this ratio stays, so we have xp over zp, because that's equal to tan theta p, and that's z0 over mu minus xr over zr times z0. And we also have that z3 is just equal to zo over mu. And again, so mu is equal to lambda 2 over lambda 1. Okay? All right, so so we have a hologram that's formed with, again, plane waves and reconstruction, and we have an off-axis point source there. So now we want to consider reconstruction with lambda 2 and some bandwidth, delta lambda 2. So this could be, say, the LED, or it could be even, say, a white light source. All right, so now what we need to know is how do these coordinates for our paraxial image point change with a change in wavelength, okay? So what we need to calculate is the derivative of x3 with lambda 2, okay? So if we do that, we end up with minus xp over zp, which is tan theta p, times zo over mu times 1 over lambda 2. Remember, mu has in it lambda 2 over lambda 1. All right. So rearranging these, what we really want to know is what is that, right? We want to know what is the delta x3. And so this is xp over zp, zo over lambda 2 over lambda 1, which is mu times 1 over lambda 2 times delta lambda 2, the spread in the reconstruction source. Okay, and then similarly, the longitudinal spread in that paraxial image point is going to be dz3 d lambda 2 is equal to minus zo over mu times 1 over lambda 2. All right, so this one is even simpler. Delta z3, that spread, is equal to zo over lambda 2 over lambda 1, 1 over lambda 2 times delta lambda 2. Okay. All right, so we have to be a little realistic about this reconstruction. You know, we can't, I mean, you could, but say, you know, if you're forming a hologram and reconstructing it, you could have, you know, lambda 2 is relatively close to lambda 1. And if that's the case, then we can kind of get rid of these ratios. We'll keep this. We can kind of get rid of these ratios. And so with that assumption, if we have a source that's sort of close, we'll then have delta x3 is xp over zp zo delta lambda 2 over lambda 2. So we have this relative bandwidth, or normalized bandwidth relative to the, say, center wavelength, and we have a delta z3 is equal to zo times delta lambda 2 over lambda 2 again. All right. So notice right away that if zo were close to 0, then the delta x3 and delta z3 are also equal to, they'll be close to 0 because they're just proportional to that object distance is away from the hologram. And so that, again, is the motivation for that, that image plane hologram, that if you keep that delta z small, delta z0 small, you can really minimize aberrations, even if you have a broadband source involved in the reconstruction. Okay, so that's a very useful tool to use. So let's do a little example. I think there's an example on the homework set too. So this will be somewhat similar. So here we'll take a hologram, kind of similar to what we had before, and here we'll keep it real simple. So we have both R and P are both at an angle of 30 degrees, plane waves relative to our film, Z and X there. And so here we'll have lambda 1 is going to be equal to 514.5 in argon line. So again, we still need a laser to record the hologram. So this might be the case for the recording using an argon laser. And then for the reconstruction, that's construction, reconstruction, we'll use a mercury arc lamp. And here we have lambda 2 is 546 nanometers, and we'll have a delta lambda 2, which is about 5 nanometers for that source. All right, so again, lambda, again, so this is an example of, you know, lambda 2 being kind of equal to lambda 1, or pretty close to lambda 1, enough so that this ratio, lambda 2 over lambda 1, is, you know, not too different from 1, basically. All right, you know, not factor of 2, but, you know, maybe 1.2 or 1.15 or something. Okay, so so now we want to know, so the question is, how far can we place the object so that we get a blur delta x3, which is less than 500 nanometers, less than or equal to half a millimeter. Okay? So that's the question. So we could solve that, right? So if we take our relationship that we have here, we have all these parameters, all the numbers already, so it's not too difficult. So we just have z0 is lambda 2 over delta lambda 2 zp over xp times delta x3. Here we have the value for delta x3. Okay, and so that turns out to be a z0 of 94.57 millimeters. So, you know, about 10 centimeters or so, right? So not, you know, pretty far away, a couple inches, several inches away we can get away with. So we don't have to straddle it really close. I mean, it could be an extended object. So you can have some depth to that object and still get some decent imagery. And then similarly, we can calculate what the corresponding longitudinal blur will be. So there we have delta z3 is equal to zo delta lambda 2 over lambda 1, and we use zo, what we just calculated, and this works out to be about 0.924 millimeters. So it's bigger than the lateral. It's almost a millimeter. It's almost twice the value for the lateral blur. Okay, so we will get some axial blurring of that image during the reconstruction. Okay, so again, these paraxial imaging relations, just like in refractive and reflective optics, are really handy and very useful to figure out lots of different things without having to go through lots of different ray analysis. We will get to that to some degree, and I will go over some of the kind of the ray trace methods that are used and how different programs like Zemax use this. So before I do that, I wanted to point out another. So we have this image plane hologram as one way of kind of controlling the dispersion characteristics in the hologram. But I want to point out another problem that I actually encountered, and a solution to that. So the problem I had, one of the problems I was working on when I first came here a long time ago, was looking at optical data storage. And so people were trying to make optical heads that used lasers and so forth, and they were trying to see if they can use holographic optical elements to do that. So the lasers, so you have a Fabry-Perot laser, and so you could have several different modes operating, and things had to be inexpensive, so there wasn't a whole lot of stabilization of the laser and things like this. So you could have, say, a temperature change of several degrees here, and what would happen then is the mode spacing in that laser might be a nanometer or a couple nanometers, something like that, as a function of temperature. And so you can get a pretty significant shift in the spot that you are trying to focus that light to with, say, a holographic lens, right? So even though it was just kind of the mode hopping or mode shifting of the laser, you would still end up with a pretty significant change in the image location. So you can, so you have this dispersive element. And so what I was interested in was just to keep that spot in the same location. I wasn't too worried about the aberrations so much. You know, the aberrations were, you know, they were not that severe. It was mainly this, you know, as this figure illustrates here, we were getting, you know, a huge movement of that. And if you're trying to focus this down onto a data disk, you know, that's a pretty large change. You're not going to be able to do it too well with that holographic element. All right, so there was a nice solution to this that's based on using grading pairs. So just like, you know, when you do lens design, you can use glasses with different V numbers, you know, high and low V crown and flint glass and stuff like that. You can do the same thing with holograms, except the dispersion properties are a bit different. But you can still use these compensating pairs of materials, or in this case of gratings, in order to correct for some of these chromatic aberrations that you get. So let's look at this from, you know, these are just things that we've learned and know about. So here we have we'll call this H1 for our hologram 1. And we have a wavelength coming in here. So here we have lambda 1 coming in, and let's say it diffracts off at a nice angle of 30 degrees. And so that's at lambda 1. All right. Then we come in here with lambda 1 plus delta lambda. Okay, so this might be our lambda 2. And as we know, we're going to get a change in that position. So we might have lambda 2 that goes like that. All right. So let's form our hologram with this normally incident plane wave, and we have an object wave that's off at 30 degrees. So, and we'll form this with a lambda 1, which is a half a micron, and we have our theta d here is theta d is equal to 30 degrees, and theta 0 is equal to 0 degrees. All right, so we have that sine theta 0 minus sine theta d. Our grading equation is lambda over the period. So here we have lambda 1. And so with this, we end up with the period. Okay, so we'll allow for, you know, a negative order here to make that negative sign, because this will go to 0, of course. So the period is a half micron, right? Because this is a half a micron. And so that's our period. So we have that grading, and it's the same grading. We now illuminate it with, say, lambda 2. And lambda 2 is going to be equal to 0.525 microns. All right, so shifted by 25 nanometers. All right, so pretty big shift there. Okay, and so it's the same grading, right? And we could use, and we have the same period. And so now the sine theta d prime that we have is equal to, again, it's also at normal incidence for that beam. So that's going to be 0.525 over 1 micron. Right? So that's equal to 0.525 instead of 0.5. All right? So now let's do the following. So we take and we make an identical hologram, all right, and put it in series here with this first hologram. And so now we come in with lambda 1 and lambda 2. So lambda 1 comes out like that, and lambda 2 comes out like that at a slightly larger angle, right? And so now, so we have, with lambda 2, we're going to have, again, sine theta d prime minus sine theta 2. Again, this is identical, so we have H1 and H2. So we have sine theta 1, or sine theta d prime minus sine theta 2. This is the new diffracted beam. And that's equal to, again, 0.525 micron over 1 micron. And so sine theta 2, it's a lot of writing, I probably didn't even need to do all that. Sine theta 2 is equal to 0.525 minus 0.525, or 0. All right, so the angle that this beam comes out at is 0. Okay? Even though the wavelength has changed, and this one here is also going to come out at 0, right? The one at 30 degrees, because that's how that hologram was designed. All right, so you get a shift, you get a lateral shift here to some degree of those two rays, of those two beams, but the beams both come out parallel to that z-axis, okay? So you might, again, so you might ask, well, why put the holograms there? If you have a beam coming in along the axis, just eliminate the holograms, and you have a beam going out along the axis, right? Well, the problem is, if we want to make a hologram like a focusing element and keep that spot from moving around, okay? Because now, instead of just having a planar hologram there, what if we now put a second hologram? So here we have, say, some diffracted beam coming off like that. And here we have a holographic lens. So we're going to have, again, this now serves as the reference beam, and we have so here's H1, and this is our HOE, holographic lens. So now, if we look at that, here's our diffraction angle here from this one, which is our reference angle or reconstruction angle for the holographic lens. So now this ray, which is the center of our spot, is always going to stay fixed, okay? That center ray is always going to stay right along the axis there, all right? And so we actually did that. And so here, here is a little spot diagram. If we change the wavelength by 10 nanometers, corresponding to this temperature-induced change that we had there, we end up with this spot which moves considerably in the image plane. If we then use a cascade of two gratings, here's this is a 1 centimeter focal length holographic lens. That spot, even with this 10 nanometer change, stays pretty fixed. And here you can see it here as well. I mean, the blur is, again, 40 microns, but it's not jumping around. And actually, this here was for a 5 degree centigrade change in the laser temperature, and this was with a 10 degree change. So even with that large change, you end up with a kind of a stationary spot, which doesn't jump all around. It's still aberrated, but there are some, actually, there's some methods, not using a sort of an analog hologram like we have, but there was a nice paper by some Japanese engineers that did a detailed computer-generated hologram calculation, so you can actually minimize the blurring due to aberrations, due to some of the aberrations in that spot. So there are some techniques to improve upon this even further with kind of digital computer-generated holograms. Okay? Yeah?
Will this work over wide range of wavelengths? Visible, right?
Well, it will work up to a certain range. The problem is you end up getting this lateral shift. So what you may end up seeing, even though the image is maybe clear, or not jumping around and so forth, but you'll get a kind of a range of colors. So you may see like a rainbow effect in your, because again, these are lambda 1 and lambda 2 here. So you you can kind of get a range in wavelengths. Later we'll talk about a form of this called a rainbow hologram that Steve Benton invented to allow you to view transmission holograms that are not image plane holograms with white light. And so what he did there was to kind of throw away the vertical parallax because your eyes are in the same plane, so you're not too worried about, you know, looking this way so much. You're mostly worried about looking directly at the object, and so you would end up getting a single small range of wavelengths. So Steve very cleverly designed this so that you take advantage of, you know, your normal viewing situation where your two eyes are separated horizontally rather than vertically, and so you can take advantage of that to eliminate, throw out some of the blurring that occurs vertically, and get a nice stigmatic image in the viewing horizontal viewing range. So, but there is, you know, I'm sure there's a limit to what you can do with this. But if you, again, to first order, you'll be able to compensate for these wavelength differences. There was another paper by a guy named DeBito back also in the 1960s, and he actually, I think he did use this in white light for viewing holograms in white light with a pair of gratings, a matched pair. And so the matching would most likely occur near the center. So if there was some variation in period with distance away from the axis, I would think that would be the cause of some image degradation as you move and change wavelengths. Okay, so I think that would be the limit. If you have two planar gratings, I don't think you would have an issue. You would just get a nice separation of all the wavelengths, you know, in the reconstruction. Okay, which might be useful for something if you're. Yeah, that's a good thought.
Patents by Canon for diffractive lenses.
Pardon?
Patents by Canon, they use two diffractive surfaces to produce high efficiency, diffraction efficiency over the whole visible range.
Okay.
To
Yeah, I think again. So I think that builds on that that paper that was published by that I mentioned by some Japanese engineers to actually do that over a wide range. But there you have to do kind of a detailed match for each illumination point and diffraction angle that you have. So you have to kind of do an iterative process across the full aperture in order to get that compensation correct, and for each wavelength. So it's a little more involved than what I'm showing you here. This is kind of a quick and dirty compensation method. But you know, this actually, you know, as I'm thinking of this, this could actually be very useful. And we did use a form of this in this imaging system that our group is working on to kind of, we needed to have a spectrally separate the wavelengths in the object area so that we could utilize this selectivity of the volume hologram, which would degrade if you didn't separate the wavelengths. If you had all the wavelengths in the object space, you can get a multitude of Bragg matching conditions from each point in the object. If you separate the wavelengths like this, then you have only one Bragg matching condition for that wavelength at that particular object location. So this again is a pretty nice technique for doing kind of structured illumination kind of applications. Okay, all right. So now let's talk about aberrations a little bit. We have a little bit of time left, and so the aberrations again are you know, similar, structured similarly to what you probably have encountered in some of your refractive geometrical optics classes. So basically what we have is a So what we're talking about, this phase for the field that we have, say phi3, 1, and phi4, 1, for our primary and secondary image phase, gives us, so this gives us a paraxial image point x3, y3, and z3, and x4, y4, and z4. Okay, so these again are the paraxial image locations. But how, that was actually formed again from that binomial expansion that we had. And for instance, we had a phase of, say, the object field in that, this was that referenced phase again. So we had 2 pi over lambda, 1 over 2 z0, and this was the form for the object phase that gave us the paraxial images. And so here we had x squared plus y squared minus 2xxo minus 2y yo. So again, so this was that 1/2 b. So we had 1 plus 1/2 b in the square root of 1 plus b. Remember, that was our expansion. And we kind of threw away the other terms in that. All right. So what you do next is you don't throw away the next term, right? So the next term is a minus 1/8 b squared, right? So in our case, this works out to be, I'm not going to do the whole thing because it's horrendous, 1/8 z cubed, and then I'll just do the first couple terms are to the 4th power. So you have x to the 4th, y to the 4th. And again, this corresponds to the phase of the field. So we have the 4th term for the wavefront, which gives us the 3rd order aberrations, ray aberrations, right? And a couple of the other terms are 2x squared, y squared, and so forth. So these are all 4th order. And we will, so again, so that is kind of building on this. So again, this square root of 1 plus b, 1 plus 1/2 b minus 1/8 b squared, and so forth. And so now we're going to keep this term and kind of throw away the higher order terms. So if we wanted the 5th order terms, we can get the 5th order, and so forth. So we can continue this process as long as we want. Usually, again, the 3rd order terms are good enough, okay, for our purposes. All right, and so what we have then is you can think of this as we have like a paraxial image point out here. Okay, which is formed by this term here. So this again gives us our paraxial image point. Out here again, so that could be, say, again, x3, y3, z3, or x4, y4, z4. And then, what we end up with this 3rd order is we have some other, our actual, the total phase that we have is some arbitrary phase, right? And so what we're doing now is looking at successive approximations to this arbitrary phase that we have here. So we're now going to include the 3rd order term in that and use that to formulate a set of spherical aberration coefficients, just like you do in refractive and reflective optics. Okay, so we'll see you on Thursday. So Thiago came in, I guess.
Yeah, I got homework this week and lab loss.
Okay. And then if anybody had questions, I mentioned, our revised grading rubric that we might apply.
Actually, there's nothing that has
grading, but for my part, but the grades for the second homework were significantly better. Average was like 94. The first homework, if you see the solutions, you see, you know, maybe if you have questions, I think that's the best way. If you have a question about your
Yeah,
homework,
that's what I told them, if they have
Yeah.
questions, to just talk to you.
just
Okay. Great. Is it still raining out?
Should we turn it left too?
When's the lab due?